Let's take a look at this smaller version of problem 11 from homework 2.1. Because we're multiplying by a diagonal matrix, and diagonal matrices are interesting. So here the only non-zero entries are going to be on the main diagonal. So we'll have zeros on all the off-diagonal matrices. Problem 11 has a 3 by 3 diagonal matrix, which is 5, 0, 0, 0, 3, 0, 0, 0, 2. Or by columns, 5, 0, 0, 0, 3, 0, 0, 0, 2. I just took a piece of that matrix D. If I want to multiply A times the matrix D, I get 1, 3, 2, 4 times 5, 0, 0, 3. And what we find is that multiplying a diagonal matrix on the left, on the right of the matrix A, is that this 5 is going to pick out the first row of A. Let's just multiply. 1 times 5 plus 2 times 0. That's all these zeros is what's going to make the interesting stuff happen. 1 times 5 plus 2 times 0 is 5. Then if I multiply 1 times the first row by the second column, 1 times 0 plus 2 times 3 is 6. So second row's first column, 3 times 5 is 15. And then 0 times 4. 3 times 0 is 0, plus 4 times 3 is 12. So what we see happened was that 5, 0, 0, 3, that diagonal matrix, multiplied the first, when I put it on the right side of A, I multiplied A by 5, the first column of A by 5, and the second column of A by 3. I kept thinking of extra things, so that's why the sentence kept derailing. I'm trying to think about something to go, oh, you forgot to, you forgot to, so I kept having to back up and then derail myself in an entirely different fashion. So if I name the columns of the matrix A as, say, A1 and A2, like we do, notice that multiplying the matrix D on the right side, I have 5, 15. This first column is just 5 times A1. And the second column is just 3 times A2. I just multiply, when I put a diagonal matrix on the right side, it multiplies the columns. This is just because of how matrix multiplication works. If I switch these around, here I can switch the order of the matrices because they're all 2 by 2, everything 2s. If I multiply D times A, that is, if I put the diagonal matrix on the left, and I'm going to do some dot product multiplication because it's faster to get through. So I'll do 5 times 1 plus 0 times 3. So that'll be 5 still. But now when I go across the next one, I get 5 times 2 is 10 plus 0 times 4. So 5, 10. And then the second row, first column, would be 0 times 1 plus 3 times 3. That'll be 9. And the second row, second column will be 0 times 2 plus 3 times 4, or 12. So now we haven't multiplied the columns of A by the entries in D. We multiplied the rows of A by the entries in D. So if I name the rows of A row 1 and row 2, then putting the diagonal matrix on the left of A will be 5 times the first row and 3 times the second row. Any questions? That was the interesting thing that's going on with 11. That's the interesting thing about multiplying by a matrix. That's the local interesting thing when it comes to multiplying by diagonal matrices. Any other questions on the problems from section 2.1? So in problem number 2, which part? We've got A plus 3B, which is defined because A and B are the same size. So one of the things that we want to notice one of the things that we want to notice is that when we want to add a couple of matrices, they have to be the same size, because that's just the rule for addition. We only add things that are the same, and when we add them, it doesn't change what they are. That's what addition means. So in problem 2, you want to compute EC. So in 2, 1, 2, we want to try to compute EC, which is E, -5, 3, times C, which is a 2 by 2 matrix. 1, -2, 2, 1. And here, we have to check if this is even possible. E is 2 by 1, but C is 2 by 2. So I cannot multiply. The number of columns of E is not equal to the number of rows of C. Undefined. So this product is undefined. The number of the columns of E is not equal to the number of rows of C. Columns of E, sorry, the number of columns of E is not equal to the number of rows of C. So the product is undefined, and we're done. If we want to multiply a 2 by 3 matrix by a 3 by 2 matrix, that will be defined because the number of columns of the first matrix is equal to the number of rows of the second matrix. And the result will be a 2 by 2 matrix. Problem 28. So in 28, if U and V are in Rn, how are UTV and VTU related? How are UVT and VUT related? So U and V are going to be vectors in Rn. So let's write those down. Let's see what happens. So 2, 1, 28. So I've got a vector U, which is in Rn. So I'll call it U1, U2, up to Un, and V, which will have n entries as well. So I'll call it V1. Oh, these aren't vectors. How could you not stop me from labeling my entries as vectors? That's minus 1,000,000 points for everybody. Back to the beginning. So I got these two vectors. And I have a couple of products that we want to calculate. U transpose times V. So U transpose, I also want to think of U as a column. Didn't want to do it this way, but I forgot this question is all about transposes. So if I want to multiply, so U we can see is an n by 1, and V is also an n by 1 matrix. So if I want to multiply U transpose is going to be U1, U2, Un. U transpose is going to be 1 by n. So I can multiply U transpose times V, and it will just be the dot product of U and V. So U transpose U transpose times V will be U1 V1, U1 V1 plus U2 V2 plus all the way out to UN Vn. And we just end up with the dot product of U and V. U transpose times V is equal to the dot product of U and V. Notice that we took a 1 by n and multiplied it by an n by 1, and the result was a 1 by 1 matrix, or a real number. So let's look at some other things. We want to look at how VTU is related. So let's calculate VT times U. So V transpose is going to be the 1 by n matrix V1, V2, Vn. And so if I do V transpose times U, I get V transpose, I'm going to write it down, V1, Vn, times U, which is U1 all the way down to Un. I end up with U1 V1 plus all the way out to UN Vn. So we see that V transpose times U is equal to U transpose times V.
Excuse me, we cannot see the board.
Oh, thank you. There, I wasn't trying to do secret writing. So if we take V transpose, which is, V is an n by 1, so V transpose is a 1 by n. And U is an n by 1. We can multiply because columns of V transpose are equal to the number of rows of U, and the result is 1 by 1. Notice that we got the dot product of U and V again. So we see the relationship between U transpose V and V transpose U is that they are equal. We see that U transpose V is equal to V transpose times U, and that's equal to the dot product U dot V. And this makes sense because the dot product, even though matrix multiplication is not commutative, the dot product is commutative. So this is the relationship between U transpose V and V transpose U. The other quantities that we were asked to calculate are U times V transpose. So let's take a look at U times V transpose. So U is this column, U1 down to UN. And V transpose is going to be a 1 by n. So V1 out to Vn. So first of all, can we do this? U is an n by 1, and V transpose is a 1 by n. So we can. So we want to multiply the first row of U times the first column of V. So I get U1 times V1. What did I write wrong? Did I write something wrong? No, it's fine. Then the second row, wait. Someone help me out because I just like brain farted. Let's suppose that U is 2, 3, and V is 5, 4. Then U times V so then U transpose is going to be 2, 3, and V transpose is going to be 5, 4. These kind of embarrassing things happen when it's the first class after a test, because It's like you finish grading the test and you're like, oh, now you should think about new stuff. But then you just graded a test, so you're like, oh, nah. So if I want to do U times V transpose, is this even defined? So if I take U times V transpose, so U is U is 2 by 1, and V transpose is 1 by 2. So we should be getting a 2 by 2 matrix. First row, first column will be 2 times 5, first row in the first column. First row, second column will be 2 times 4, which is 8. And then the second row, first column will be 3 times 5. And then the second row, second column will be 3 times 4. Oy. Sorry, I had to take a detour into numbers, and the reason that I was really messed up was because I only wrote 2 of the entries in here because I was being lazy. So once again, being lazy really messes you up. So I take U1 times V1, then the first row, second column of the product will be U1 times V2. And then that will go all the way to U1 times Vn. Then the second row, first column in the product will be the dot product of the second row of U and the first column of V transpose. So that'll be U2 V1, and then U2 V2, all the way up to U2 Vn. And this will go all the way down to Un V1, Un V2, all the way out to Un Vn. So now that we've calculated U times V transpose, we can see all these products. We get an n by n matrix. Just like when we take a 2 by 1 by a 2 by 2, we get a 2 by 2 matrix. Let's calculate V times U transpose. So if we do V times U transpose, I'm going to have the matrix V, V1 up to Vn, times the matrix U transpose, which is U1 Let me try that again. I'll take the matrix V, which is V1 down to Vn, and the matrix U, which is U1 out to Un. So in my resulting n by n matrix, I'll take the first row of V and the first column of U transpose. So U1, V1 again, or V1, U1. Then I'll take the second row of V times the the first row of V times the second column of U transpose, V1, U2, all the way out to V1, Un. Then I'll take V2, the second row of V, and multiply each of the columns of U transpose. So it'll be V2, U1, V2, U2, all the way out to V2, Un. And then so this will continue on until we get to Vn, Vn, U1, Vn, U2, all the way out to Vn, Un. So what we see is that instead of the U's, I get U1 V1, then U1 V2 down to U1 Vn. Instead of that showing up as the first row of VU transpose, that is the first column of VU transpose. So what we notice is that UV transpose is equal to the transpose of V times U. And this is a fact that we know about transposes. The product of a transpose, the transpose of a product is a product of the transposes in the reverse order. See, I was thinking of that the whole time, so that's what was messing me up, trying to actually calculate the little bits inside. Any questions? Great. So in general, we were using this fact. The transpose of a product is a product of the transposes, but in reverse order. The transpose of a product is the product of the transposes in reverse order. So in problem 12, what are we looking at? In problem 12, we have a matrix A, 3, -2, -6, 4, and we want to construct a 2 by 2 matrix B such that AB is the zero matrix. Use two different non-zero columns of B. So A is 3, -2, -6, 4, and we want to find B is 2 by 2 non-zero matrix with different non-zero columns such that A times B is equal to the zero matrix. I'm gonna write it out. 0, 0, 0, 0. So this is also an important problem that we have to think about, because I'm going to take a non-zero matrix A and multiply by another non-zero matrix B and come up with 0. This is matrix multiplication. It's got a bunch of addition combined in there, addition inside. So this is different than than multiplication that we're familiar with. When we're multiplying real numbers, if one of the factors is 0, then the product is 0. But in matrix multiplication, we can have two non-zero factors producing a 0 product. So if I think of B as the matrix with B1 and B2, and we're going to note B1 is not equal to B2, and neither one is the 0 entry. If we think about the product A times B and think about the columns of B, so AB will be A times the columns of B, B1 and B2. So we'll have the matrix A times B1 and A times B2. And we want this to equal 0, 0, 0, 0. So we got to ask ourselves, is this even possible? And why is it? And if so, how come it's possible? So look at what this tells us. The first column, A times B1, has to equal 0, 0. So this means A times B1 equals the 0 vector, and A times B2 is equal to the 0 vector. So let's think about what this means. I want to have A times B1 equal to 0 vector. I want a solution to this homogeneous equation. And I want a non-zero solution to this homogeneous equation. What we need, B1 and B2, are two non-zero solutions to the homogeneous equation A times AX equals 0. So note, B1 and B2 are two different non-zero solutions to the homogeneous equation AX equals 0. What is it about, is this possible, and how can we tell? So let's pause for a second. Think, is this possible, and how can we tell? Is it possible that AX equals 0 has a non-zero solution? Why is it possible? How can we tell that this is possible? How do we know such solutions exist? Opposite of that. The columns of A, the second column of A is just -2 times, it's okay, I do it all the time. I have to repeat most of my sentences because I say the opposite of what I wanted to say, which is super confusing, I'm sure, to people like listening or just trying to follow along. So the second column of A is just -2 times the first column of A. The columns of A are linearly, opposite of that, are linearly dependent. The columns of A are linearly dependent. And we can tell because A does not have a pivot in each column. And we can tell that because the second column of A is just a multiple of the first column of A. So the columns of A are linearly dependent. We know this because there are only 2 columns, and the second one is a multiple of the first one. A2 is just -2 times A1. We could say that A does not have a pivot in each column. If we found the reduced or echelon form of A, what's the reduced or echelon form of A? I'll do the hard part, 1, 0. The second column is just -2 times the first column, so the second column will be -2, 0. Perfect, thank you. So A does not have a pivot in every column, so the columns of A are linearly dependent. That means AX equals 0 has a non-trivial solution. And if an equation, since we do not have a pivot in every row, since we do not have a pivot in every column, that means the equation AX equals 0 has infinitely many solutions. So there's a lot of things that are connected with this little observation. So we know we can find B1 and B2 because there are infinitely many solutions to the equation AX equals 0, because the columns of A are not linearly independent. So as far as finding B, just find 2 different non-zero solutions to AX equals 0. Now, when I say 2 different non-zero solutions, that just means they can't be equal. They can be multiples of each other. We're not going to be able to find, because the solution set to AX equals 0 is one-dimensional, because there's one free variable. They don't have to be linearly independent. That's not possible in this case. They just have to be different. So if one of the answers is 3, 0, the other one can be 6, 0. Those could be your columns. Those are your 2 different non-zero solutions. Any questions? This one's tricky because you have an infinite number of solutions. So they're all going to be writing different things. So there were some other questions. So in 18, if the third column of B is all zeros, and I multiply A times the third column of B, then the third column of AB will all be all zeros. Just think about if if we multiply A times B, and B has a column of zeros, so it looks like B1, B2, and then 0, a column of zeros. Then I'm going to have A times B1, whatever that is, A times B2, and then 0. Because A times 0 is equal to 0. In 21, the last column of AB, suppose the last column of AB is entirely zeros, but B itself has no 0 columns. The last column of AB is 0, but B itself has no column of zeros. What can be said about the columns of A? So what we have here is that, this is in 18. So in 21, we have the last column of AB is 0. So A times B1. So, and we get 0 here. So what we're saying is that A times B, P, n rows and P columns. A times BP is equal to 0. But B has no non-zero columns. So the last column of AB is equal to 0, but B has no 0 columns. What this means is that BP is a non-zero solution to AX equals 0. So what we are being told here is that BP, the pth row of B, is a non-zero solution to the homogeneous equation AX equals 0. So we have found a non-zero solution to the homogeneous equation AX equals 0. What does that mean for the columns of A? Oops, I can scroll down. The columns of A are linearly dependent. So therefore, the columns of A are linearly dependent. Because we have found a non-trivial solution to the homogeneous equation. So the columns of A must be linearly dependent. Any questions? So if A is m by n, do the columns of A span Rm? Span Rm? If I said A is m by n and B is n by p. So we found out that the columns of A are linearly dependent. Do the columns of A span Rm? If not, why not? And if so, then why? We have one vote for no. Does anybody else agree? Well, we've got a no and a yes. Now we have controversy. So, since the columns of A are linearly independent, what can we say about the pivots of A? The columns of A are linearly dependent. What do we say about the matrix A, the pivots of A? This is D&D bonus material, or DVD bonus material now. So A does not have a pivot in every column. Since A does not have a pivot in every column, tell me about the pivots in the rows of A. Scroll, 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 scroll. Well, I think. If by your silence you mean we can't tell anything about the pivots in the rows, you are correct. We don't know anything about the pivots in the rows. I told you that A is m by n. I don't know if, I know there's a non-pivot column, but that does not mean that there's a non-pivot row. So we don't know anything about the rows. Not a but, about. We know nothing about pivots in rows. It could be that there's a non-pivot column and there's still a pivot in every row. It could be that there's a non-pivot column and there's not a pivot in every row. That would depend on the size of A. All we know is that A has n pivots, but we don't know how n compares to m. Or sorry, it has fewer than n pivots. Oh, wow, I didn't write the letter A. A has fewer than, I missed the letter A again. You all should be very concerned that I, for some reason, stopped writing the letter A. A has fewer than n pivots. But we don't know how m compares to n, and so we don't know anything about the pivots in the rows. So the reason that I asked that question of opportunity is that some of you were talking about the columns of A spanning Rn because the columns of A are linearly independent, and those two things do not go together. I think some of you were looking at the invertible matrix theorem, which has the following are equivalent. And one of the lines of the invertible matrix theorem, it says the columns of A span Rn. And the other thing it says is the columns of A are linearly independent. But there's a lot going into that. That's when A is a square matrix, that's the big one. And it is also invertible. Now, if A was n by n, if A is a square matrix, then having fewer than n pivots means we don't have a pivot in every row. But if A is just some other rectangular matrix, then we don't know. We can't talk about the rows. And so let's look at 22. If the columns of B are linearly dependent, then so are the columns of AB. So that's a good one to look at. If the columns of B are linearly independent, the columns of AB are also. Now, the key thing here, the key thing in this particular problem is that we want to think about how we characterize the columns of B being linearly dependent. So we got to think of what it means for the columns of B to be linearly dependent. Let's first of all establish some stuff that we can work with. Let's let A be m by n, and let B be n by p. All we know is that we can multiply A times B. That's all that we're given, because they said, show that the columns of AB are linearly dependent. That means we must be able to multiply AB. If the answer was like, oh, what if B has the wrong number of rows? Then this is not even a question. And that would be a dumb question. If that's the answer to your puzzle, then you didn't write a good puzzle. That's the linear algebra version of saying, the butler did it. And like your reader's looking back, saying, well, the butler hasn't even been a character in this whole thing. That's a dumb twist. So we know that AB is defined. So the columns of A must equal the rows of B, but we don't know about the rows of A or the columns of B. And I'm also going to I'm going to name the columns of B because it's the second one. So let B be B1, B2, all the way out to Bn. We're just establishing some stuff that we can work with. All right. So what we have is the columns of B are linearly dependent. What does it mean when we say the columns of B are linearly dependent? Someone tell me what that means. The columns of B are linearly dependent. How do we characterize linearly dependent sets of vectors? Linearly independent would mean that there's a pivot in every column. So linearly dependent means that B has a non-pivot column. So opposite of that. I do it all the time. We're in class. This is why we get on a test, when we're typing things, before we hit submit, we definitely want to be like all proofreading, but here we're just like typing real fast. So the columns of B are linearly dependent. So B has a non-pivot column. That's one thing. Let's see. Columns of B are linearly dependent. So what's that mean? B has non-pivot column. There's not a pivot in every column of B. What's another way we can characterize the columns of B are linearly dependent? Not quite. We have more than two vectors here. So we can't just say constant multiples of each other. That might not be the case because there's more than two. But what's the more than two version of that? So that's close. Linear combinations. One of the vectors is a linear combination of the others, which means they're linear combinations of each other. But specifically, one of the vectors is a linear combination of the others. One of the columns, missed off the N. One of the columns is linear combination of the others. I'm thinking of one other characterization of linearly dependent sets, one that we've used right on this page. There's one other one that I could think of. Think in terms of equations. So one of the vectors is a linear combination of the others. B has a non-pivot column. B does not have a pivot in every column. A times B has infinite. That's close. I don't want to multiply A times B equals 0. I want to specifically talk about the columns of B. There's the homogeneous equation. Non-trivial solution is part of it. The homogeneous equation, B times X equals 0, has a non-trivial solution. The homogeneous equation, Bx equals 0, has a non-trivial solution. So these are all characterizations. These are all characterizations of the columns of B being linearly dependent. In this case, the last one is probably going to be our best route in. I would think the last one is going to be the best route in, or the second one is also a good route in, although it's harder to state in this case. Also, BP, not BN. All right. So we've taken what we're given. B, the columns of B are linearly dependent, and we want to show that the columns of AB are also linearly dependent. So here's the other piece of evidence that we have in effect. We want to think about how matrix multiplication works. So we've got a couple routes for our given information. Now we want to note that if A is m by n and B is n by p, then AB is equal to A times all the columns of B. B1, B2, fixed, up to BP. And to get that, I just make linear combinations of the columns of A using the entries in the columns of B as weight. So that's going to be A, B1, A, B2, out to A, B, P. So I want to specifically look at the columns of AB because we're trying to show that the columns of AB are linearly dependent. So we want to show and we have a choice of things. We want to show that AB does not have a pivot in each column. So AB has a non-pivot column. This one is tricky because we don't really know about the pivots because we have generic names for columns, but we don't have numbers for what they are. So pivots are going to be very difficult to work with here. One of the columns of AB is a linear combination of the others. That might be workable. And then the third thing, we'll want to show that the homogeneous equation AB times X equals 0 has a non-trivial solution. If we can start with the fact that the columns of B are linearly dependent and show one of these three things, then we'll be able to conclude that the columns of AB are also linearly dependent. And now that I've written the three possibilities out, you can see why I really liked that last one, that homogeneous equation having a non-trivial solution. All right. So what you want to do is create an argument where you take a non-trivial solution of Bx equals 0 and show that it is also a non-zero solution to AB times X equals 0. So that's your strategy. Claim non-zero solution to Bx equals 0, and then justify that statement. Then use that same non-zero solution is solution to AB times X equals 0. Since Bx equals 0 has a non-zero solution, that same solution will work as a non-zero solution to AB times X equals 0. Therefore, you'll be able to conclude that the columns of AB are linearly dependent. So the tricky part of this problem is not knowing what it means for a set of vectors to be linearly dependent. It's knowing that everything that means. It's not about knowing what linear dependence means in one definition, but all the definitions, and then deciding which one is going to be most useful. Any questions? This is not a complete proof. You're going to have to write the details. Y'all are going to need to write out the details for this. But that's a roadmap to how this should work. I'm not from the South. I just say y'all because it's less pointed than you. Any questions? All right, let's pause the video and talk a little bit about invertible matrices.